Today, once again, it's your man Chiefs, moving on with work energy and power. This is our second session. I remember the last time when I was talking about work energy and power, I asked you to think about kinetic energy. Kinetic energy as being the energy a body has due to its motion. So everybody that is in motion has got kinetic energy. It is given the symbol EK and calculated as half mv squared. So kinetic energy is affected by the body's mass and the body's velocity. All right, so kinetic energy EK is equal to half mv squared. Okay, how about potential energy? Potential energy is the energy a body has due to its position in relation to the surface of the earth. So for example, if an object is high up, all right, in relation to the surface of the earth, we can say that that object A has got more potential energy compared to object B of equal mass due to their position in relation to the surface of the earth. So, calculating EP, we multiply the mass of the object times g, which is gravity 9.8, times the height above the ground. Very important to remember. When an object has energy, it is able to do some work. In other words, if it has potential energy, it's able to fall, right? If it has got kinetic energy, it's able to move, right? When work is done, energy is transferred between systems. Work and energy are different forms of the same quantity. Energy may be transferred in the form of heat, sound, chemical, mechanical energy. We'll talk more about mechanical energy a little bit later on. Work done against friction often generates heat. So when there is a frictional force, work being done by friction often produces heat. On a cold day, you rub your hands together, that often produces heat, right? Units of energy are joules. Joules are a scalar quantity. And you can agree with me that work done, when we found out or calculated work done by objects, we also put it in joules. That brings us safely to the work energy theorem. The work energy theorem comes from F net is equal to mass times acceleration. How does that come into play? Let's think about it quickly. If we look at F net being equal to mass times the acceleration, we can consider a situation where if we are going to play around with F net being equal to mass times acceleration, and the aspect that W net, work done by net force, is equal to F net multiplied by the change in the distance. If you take this equation and try to break it apart, you can end up with F net is equal to mass multiplied by velocity final minus velocity initial divided by 2, right? Or mass times velocity initial divided by change in time, all right? Which basically is the acceleration, but that's something else to think about. Look at it in this manner, that F net is equal to mass times acceleration according to Newton's second law. And take that mass times acceleration and bring it down here. Mass times acceleration times change in x is going to give you W net. This is coming from Newton's second law. All right? According to the equations of motion, we can pick up the equation of motion that says Vf squared is equal to Vi squared, right, plus 2 multiplied by acceleration multiplied by change in x. If I am going to play around with this equation, I can write it out as A times acceleration is equal to V final squared minus V initial squared all over 2. Right? If A multiplied by change in x is representing that A multiplied by change in x in W net, you will agree with me that net force is equal to mass multiplied by Vf squared minus V initial squared all over 2. We can follow by saying a half of mass multiplied by Vf squared minus a half multiplied by Vi squared gives us the value of the net force. If you look at this, what does it show you? It shows you a change in Ek. So therefore, W net is equal to change in kinetic energy. Voila! We have shown what we now call the work energy theorem, which states that the net work done on an object is equal to its change in the object's kinetic energy. This is an equation that you also find at the back of your question paper. More work on this you can find in our revolutionary guide written by Norman Muvoti and Timothy Sibeko. All right, we must note that if the work is done in the direction of the object, it will accelerate. And what happens to its kinetic energy? If a network is done in the direction of the motion, what happens to its kinetic energy? Its kinetic energy must increase, right? If work is done in the opposite direction, let's say, for example, the object is moving but work is being done in the opposite direction, what is going to happen to the object? The object will decelerate and its kinetic energy is going to decrease. I think that's straightforward, basically. Let's quickly look at some questions and some calculation that are involving work done. Here is one example that I want us to look at. And it says that, good, a car of mass 2,000 kgs increases its velocity from 0 to 10 meters per second over a distance of 50 meters. What is the increase in its kinetic energy? So in other words, this question is asking us for a change in the object's kinetic energy. Let's go through it. How are we going to calculate it? A, the change in Ek is equal to, we are given the mass, we are given initial velocity, we are given final velocity, all right? In this instance, we don't need to use the distance that it's covering. So the Ek is equal to half mv squared. All right, because the mass is common, V final minus V initial squared. Half of mass of 2000 multiplied by final velocity of 10, final velocity of 10 minus 0. 10 squared, 0 squared. Pull out your calculator. I got my blue baby here with me. We must be able to calculate that quickly, and it must give us a half of 2000 right, multiplied by 10 squared. And our final answer is 1 times 10 to the power of 5 joules. Okay? You can change it to kilojoules. It's up to you. All right? Next question says, how much work was done by the net force acting on the car? What do we know? We know that the net force, W net, work done by the net force is equal to change in EK. What did we just calculate there? We just calculated the net force. And the net force that we have there is equal to the same value as in A, which is 1 multiplied by 10 to the power of 5 joules. There is our answer. C. Calculate the net force that caused the car to accelerate. So this question is now asking us to find the net force that allows the car to accelerate. We know that the change in EK is equal to the force multiplied, net force, multiplied by the change in X, multiplied by the cos of angle theta, which was 0, obviously, because it's moving on the horizontal. Therefore, we have got already the EK. So our F net is equal to change in EK divided by change in X. That gives us 1. So the EK is 1 times 10 to the power of 5 joules divided by the distance, which is in meters, perfect, 50. And our final answer is, pull out your calculator. Remember, your force is measured in newtons. 1 times 10 to the power of 5 divided by 50 will give you, that's an easy one, 2,000 newtons. All right, so that's a simple question here on using our understanding of kinetic energy and the work energy theorem. Questions come often in an exam. They direct you on what to use. Sometimes they say, using only the work energy theorem, find this unknown value. Please be always wary on what is required in a question for you to answer it correctly. Let us move on quickly and look at conservation of energy with non-conservative forces present. So what is a conservative force? A conservative force is a force for which the work done in moving an object between 2 points is independent of the path taken. Like, for example, when we talk about gravitational force. So, work done by gravity is independent of the path that is taken, right? like elastic force in a spring, or the Coulombic force, which we'll look at a little bit later on. These are conservative force. It is independent. It does not depend on the path taken. It's still the same. All right? And then the opposite of that is a non-conservative force. The force, a force is defined as a force for which the work done in moving an object between any 2 points is dependent on the path taken. E.g., frictional force, resistance, tension in a cord. Right? I want you to keep in mind that work done by a non-conservative force, work done by friction, or work done by air resistance, or work done by tension in a cord is equal to change in kinetic energy plus change in potential energy. Mechanical energy, I spoke about it a little bit earlier on, is the sum of kinetic energy and potential energy. We have talked about kinetic energy, we have talked about potential energy, and mechanical energy is basically the sum of these energies, kinetic and potential. When it's a non-conservative system, the mechanical energy is not conserved. In other words, in a non-conservative system, we got a value for change in K plus change in the kinetic potential energy. So that's in a non-conservative force. In a conservative force, they are equal. The kinetic energy, change in kinetic energy, or sum of kinetic energy is equal to the sum of the potential energy. All right. So remember that mechanical energy is the sum of kinetic energy and potential energy. In a non-conservative force, or when a non-conservative force is applied, we must remember that the total energy of the system is still conserved. In other words, the energy before is equal to the energy after. All right? So there could be 3 energies before producing one type of energy. Those energies are conserved. All right? That's the total energy of the system is conserved. You get to understand that a little bit more when we start looking at a few questions in light of that. Here's a question that's up on the board that I want us to look at quickly. And the question says, and I want you to think pertaining what we have discussed already. Which one of the graphs below correctly represents the relationship between the kinetic energy of a falling body or falling object and its speed? All right? The kinetic energy is on the y-axis and the velocity is on the x-axis. Let's look at our graphs. Does the first graph explain it? We know that our EK is given by half mv squared. All right? So it cannot be a straight line like that. This is incorrect. We know that as velocity is increasing, when a body falls, according to our projectile motion, if a body is falling, it is increasing in velocity. So this one is completely out because the velocity, though increasing, kinetic energy is decreasing, right? With this one, that's the correct answer. Look at it. As the velocity increases, exponentially, the kinetic energy is also increasing as a result of V being squared in this instance. Our correct answer for this question will be C. Now let's look at the next question. It says that a block of mass M is released from rest from the top of a frictionless incline as shown below. The total mechanical energy of the block is Q at the point, is EQ at the point Q and ER at the point R. The kinetic energy of the block at the point Q is, and R is K, Q, and KR respectively. The question then says, which one of the following statements regarding total mechanical energy and the kinetic energy of the block at the point Q and R respectively are correct? Let's look at this question quickly. We know that if this object is released from rest, its EK initially at this top is at its minimum, which is 0, right? When it's reaching the ground, its EK is at its maximum. In other words, its EK here will be equal to the EP, which is at its maximum due to its position above the ground. All right? The EP here, because it's on the ground, position 0 is going to be equal to 0. This EK is 0 because it's at rest. Which one of the following shows the correct answer? Total mechanical energy, E. Okay? So, if we consider at point Q, right, the total mechanical energy at point Q is equal to the total potential energy at point R. So, these ones with equal signs, one of them is correct. How about the comparison of KQ and KR? We have agreed that KR is greater than KQ. So therefore, our correct answer is right here, B. I want you to understand aspects of mechanical energy and kinetic energy and how they relate to an object moving along an inclined plane, because they are very important in our calculations of either the velocity of an object or calculating the work done by an object while moving along an inclined plane. Let's look at the next question, or the next point actually. I can't look at the next question without looking at this very important area, power, right? Power is the rate at which work is done. There we go. Tick. Power is the rate at which work is done. What have we done so far? We know how to calculate work. Yes? Work done. Anything that talks about rate talks about time. So power is the rate at which work is done. Power can also be given by P is equal to F multiplied by V. How does F multiplied by V come into play? Where does it come from? How do we get to a place where we say P is equal to F multiplied by V? You know already that work done is equal to force multiplied by change in X. Now, if I am going to substitute W, where I have got W here, by F multiplied by change in X over change in T, you also know that velocity is equal to change in X divided by change in T. Therefore, I can safely say that F multiplied by V gives me the value of P, which is exactly what you see here. So think about that and keep it in your mind that sometimes you could be given the displacement and the time and the force, and you're required to calculate power. Will you be able to do that? Of course, you must be able to do it. All right, let's look at a question quickly. Here is a question that says, I said we cannot do this question unless we know aspects of power. All right, let's consider this question that's up on the board and try to answer it. The top part is clear, so I will not need maybe to read it from here. It says the diagram below, not drawn to scale, right, shows a vehicle of mass of 1,500 kilograms starting from rest at point A. If it's starting from rest, it means initial velocity is 0. At the bottom of the rough incline, point B is 200 meters vertically above the horizontal. The total work done by force F that moves the vehicle A to B is in 90 seconds is 4,80 times 10 to the power of 6 joules. Right? The first part says define a non-conservative force. All right? We know that a non-conservative force is a force that moves, okay, is a force that does work, all right, on an object by moving it between 2 points and depends on the path that is taken, all right? So a non-conservative force, it depends on the path taken. So the question that follows, so 5.1 is defining non-conservative force, which we said earlier on. A non-conservative force, if you remember that quite well, is a force on which work done moving on an between objects between 2 points depends on the path taken. Like, for example, frictional force. All right? The next question says, is force F a conservative force? Choose yes or no. All right? So the force F here that's going to move the object up the ramp is a non-conservative force. Okay? So the answer here is no. It is not a conservative force. 5.3 makes my writing easier and I have more space for working here. 5.3 then requires us to calculate the power generated by the force F. Just as I had said earlier on, I couldn't have done this question, or I would have found this question to be slightly longer to answer if I didn't have a formula for finding power. So I said power is equal to work done over change in in time. All right? Do I know the work done? Yes, I do. The work done is 4,80 times 10 to the power of 6 divided by time of 90, right? Pull out your calculator with me and let's do the calculation. Very simple. 4,8 multiplied by 10 to the power of 6 divided by 90. All right, your final answer is 53,333,33. Okay, check again your answer with me if that's the correct answer, which is 5,33 times 10 to the power of 4. The unit of power is watts. What is the unit of power? Watt. You get it? All right, so that's one way of calculating this answer. All right, let's say for some reason, all right, you don't know, or you don't remember, or you don't want to use P is equal to W over T, and you want to use another way of calculating power. It will be a longer route, but it can help us revise certain concepts. You can go by finding the value of delta X first, which is V final minus V initial over 2 multiplied by change in T. We have used this equation before. Where did we use it? Projectile motion. So V final is 0, okay? 0 plus 25 okay? Because it's minus minus over 2 multiplied by change in C, which is 90. And you can calculate with me again. 12,5 multiplied by 90 is equal to 1125 meters. Now, you got change in X. What are you going to do with that change in X? You are going to try and find the force, all right? You're going to try and find the force. And after you find the force, you look for the P average. It will be very interesting for us to introduce the P average at this instance. So, work done by a force, F is equal to F multiplied by change in X, right? Multiplied by cos of theta. All right. The theta is equal to 0 because it's moving along the plane, right? So, what is the work done? Work done is 4,80 times 10 to the power of 6 is equal to F multiplied by 1125 meters multiplied by cos of 0. If we are going to calculate that, you can agree with me that the value of F is going to be equal to, pull out your calculator, 4,8 times 10 to the power of 6 divided by 1125. That gives us 4,266,66 okay? And this is in newtons. I'll keep this because I need to use it. Now that I've got my F, I can find my P, right? Average by saying the P average is equal to the force times average velocity. Okay? My force is the one that's up there, 4,266,66 ... times the average velocity is given by 0 plus 25 divided by 2, which gives me again an answer of 5,33 times 10 to the power of 4 newtons. Voila! There you got your answer, all right, with 3 marks. Using a different method now here to find the same value. But what have we done? We've been able to revise an aspect of Newton's law of motion. We've been able, equations of motion. We've been able to revise work done, all right? And also, I have just introduced an important aspect, which is called P average, which can be found by F times velocity average. Okay, let's move on to the next question. As you quickly copy off that and make sense of what is on the board. All right, so the question then says, the speed of the velocity of the vehicle when it reaches point B is 25 meters per second. All right? State the work energy theorem. Okay? Our work energy theorem states that the work done by an object, all right, is equal to change in kinetic energy. So we need to use, this one is specific, we need to use energy principles to calculate the total work done on the vehicle by the frictional force. We need to use the work energy theorem. So work energy theorem states that the net work done or total work done is equal to change in kinetic energy. Now, listen, if a question asks you to state something, it is often giving you a hint of what to use in the next parts. It doesn't really just say states and then that's the end of it. By stating, it scaffolds to allow you to make use of what you have stated in calculating it. So I am so sure, even before I read the next question, that the next question is going to ask me to use the work energy theorem to calculate the answer for the next question. All right, let's look at it and answer it together quickly. The question says, use energy principles. An energy principle is the work energy theorem, one of them, which says that 5.5, the W net is equal to change in kinetic energy. Now let's consider what's happening to our vehicle as it moves up the plane. And that's very important for us to think about. When it's moving up the plane, there are certain forces that are working on it. We said that forces working on it there's a component of the weight of the object. Not only that, we hear of the frictional force that's working on it. That's why they are asking us for the total work done on the vehicle by the frictional force, okay? We also have, right, so that's work done by frictional force and by the weight, and then there's the work done by the engine going upwards, all right? So, if I am going to subtract the work done by the non-conservative force, or in other words, if I am going to consider the vector sum of all the forces that are involved here, they should give me EK. So work done by weight, which comes down, plus work done by friction, plus work done by the force going up, right? It should give me the change in kinetic energy, which I already know the change in kinetic energy for this particular situation is half of mass 1,500, okay? We are given the final velocity 25, which is 25 squared minus 0. Work done by the weight is going to be the components of the weight, which is mg cos of theta times delta x, cos of theta, the angle, plus work done by friction, which is what we are looking for, and that should be minus work done by the force, which we are already given in the question as 4,8 times 10 to the power of 6. All right. So here is a simple equation. We can work it out to find WF. What do I know? I already know that I have the magnitude of 1,500, okay, which is the mass. I have got the distance of 200 change in x, and the cos of the angle is actually an angle of 180, because that force of FG parallel is 180. You can take it that way or that way to the motion of the object, cos 180 degrees plus WF, which is force of friction. Let's give it a small letter f, plus 4,8 times 10 to the power of 6 is equal to a half. 1,500 multiplied by 25 squared minus 0. Okay, minus 0. 0 squared is still 0. I am sure if you are diligent in your mathematics, you can solve that very simple equation, and you must be able to come up with the work done by the frictional force as minus 1,39 times 10 to the power of negative 6 joules. Okay, this is one way of doing it. There are several other ways of doing or answering this question, But I am so sure that as we go through more examples and more questions that are to do with work energy theorem, you will be able to establish how to work out questions like this. As for today, I'm sure you have had a mouthful. It's ciao from